Welcome back to Chemistry Lab. Today's topic, colligative properties. These are properties that depend only on the amount of solute dissolved in the solution. There are 4 of them. The first one is vapor pressure lowering, freezing point depression, boiling point elevation, and osmosis. What we mean by this is that the vapor pressure of a solution is always lower than that of the pure solvent. The freezing point of a solution is always lower than that of the pure solvent. The boiling point of a solution is always higher than that of the pure solvent. Then osmosis is a different beast altogether. In this lab, we'll be looking primarily at freezing point depression and boiling point elevation. To describe those to you, I want to look first at vapor pressure lowering. If you have a solution in a beaker, you know that molecules on the surface of solution, of those molecules, some of them will have enough energy to escape the surface of the liquid and go into the gas phase. Right? It is this pressure of the gas phase against the surface of the liquid and against the atmosphere that is the vapor pressure. In the case of a solution, you have solute dissolved in this, so on the surface of the solution, there are some solute particles taking the place of solvent molecules. In other words, there are fewer solvent molecules available to go into the gas phase. And that's why the vapor pressure of a solution is always lower than that of the pure solvent. But if we extend that argument to boiling point elevation, as you heat up this solution, we know that boiling point occurs when the vapor pressure is equal to the atmospheric pressure. So in a solution, if the vapor pressure starts out lower than that of the pure solvent, that just means that we're going to have a higher temperature in order for that vapor pressure to be large enough to equal the atmospheric pressure pushing down. That means that the boiling point of a solution is always higher than that of the pure solvent. The freezing point of a solution is always lower than that of a pure solvent because you can imagine that for water, for example, we know that water has this nice bent molecular geometry and that it takes a nice zigzag pattern when the hydrogen bonding regions line up. Right? Where one water molecule is hydrogen bonding to another and so forth and so on. So you get this nice zigzag pattern whenever water freezes. Now, if there is solute dissolved, you can think of those solute particles as interfering with this arrangement. So that means it will require removing even more energy in order for water to freeze. Therefore, the freezing point of a solution is always lower than that of the pure solvent. The equations that describe freezing point depression and boiling point elevation look very similar to one another. Change in temperature is equal to a constant, and we'll talk about freezing point right now, a constant for the solution times the molality times I, which I is called the Van 't Hoff factor. Van 't Hoff factor. And it refers to the number of ions that are released in solution. For example, sodium chloride dissociates to sodium ions plus chloride ions in water. So we would assign a Van 't Hoff factor of 2 to sodium chloride because it produces 2 moles of ions in solution for every 1 mole of solid dissolved. Molality, the little m here, is a unit of concentration, which is moles of solute per kilogram of solvent. And the K is a constant that you can look up for each solvent. Delta T is the change in temperature between the freezing point of the pure solvent and the freezing point of the solution. In the lab experiment today, you will be using this equation to solve for the Van 't Hoff factor. Now, experimentally, the Van 't Hoff factor isn't going to be what we see theoretically. For example, sodium chloride, we know we could describe theoretically the Van 't Hoff factor should be equal to 2. But experimentally, it's usually a little bit less than that because some of the ions will pair up again, and it will mean that you actually have fewer than 2 ions for that reason. So that's what you'll be looking for. You'll be solving this equation for the Van 't Hoff factor. Don't forget to answer the pre-lab questions, and have a great lab.